Hi, my name is Ching and welcome back to Data Structures in C++. In the last lecture, we talked about balanced binary search trees and how to balance them. Today, we're going to be talking about hash tables and the hashing problem. Then we'll talk about hash functions and what good hash functions should have. Next, we'll move on to collision resolutions and how to solve the hashing problem. These include separate chaining, linear probing, and quadratic probing. Let's first see an example where we need to use hash tables to solve this problem. Suppose every student has a unique email ID and we want to search for a student's grade in constant time. And we can't create a big array to hold all the possible IDs. Because, for example, if we assume IDs only contain letters and numbers, have a length of 10, are all lowercase, and the first character must be a letter, then the first letter will have 26 possibilities. Then the rest 9 characters can either be a letter or a number, so that the possibilities for each character is 26 plus 10. Multiply all the possibilities up, we get a number that's at least 2 times 10 to the power of 15 possible IDs. That's over 2,000 trillion IDs. This is too big to store in an array. So instead of creating a big array for all the possibilities, we need to define a function that maps a student's ID to a number in a smaller range. And ideally, the complexity should be constant time. But the problem is, we might have 2 or more IDs that may map to the same number. We'll see how this could happen in an example soon. Let's formally define the hashing problem. Hashing is simply the process of mapping an object to a value in a given range. The purpose of hashing is to use a much smaller range to index much bigger possibilities. Therefore, it is possible for multiple objects to get mapped to the same value in the smaller range. This is called a collision, which is a typical problem in hashing. Therefore, in addition to hash functions, we also need some mechanisms to deal with collisions. Let's start with hash functions. There are many ways to define a hash function, but not all hash functions are good. So what makes a good hash function? A good hash function should have the following characteristics. First, they should be fast, probably constant time, because this function will be called for every access of the objects. Second, the hash value must always return the same hash value each time for the same object. Third, if we make equal objects, or they're pointing to the same address in memory, such as x and y, then the hash of x should be the same as the hash of y. Last of all the hash values should be uniformly distributed. This is to avoid collisions as much as possible. Let's see an example next. Here we need to store student IDs and quickly find the grade of any given ID. As we explained previously, we can't just create an array of 2,000 trillion entries. So let's try to map those to an array of size 8. We call this array a hash table, and each row a bin. So the next task is to design a hash function, which will take an ID string and return an integer from 0 to 7, which corresponding to a bin in this hash table. For example, we have a student ID called Peter12345 with a grade of 95. So how would we store this entry in this array? Let's design a simple hash function. In this function, we only check the first character of each ID, and then we look up its decimal value in the ASCII table, which is an integer. For example, the letter P has a value of 112. To map an integer to the range from 0 to 7, we can use the modulus operation with 8. Let's see an example. In this example, we would like to save Peter's grade to the hash table. P in the ASCII table is equal to 112 in decimal. So we take that number and perform mod 8 on it. This will give us 0, which means the bin at index 0 in the table. Now I can store this entry at the bin 0. So let's suppose we want to store another entry for Charlie. In this case, we have C as the first letter. C, in this case, is equal to 99 in the ASCII table. 99 mod 8 equals 3, so we can store this entry into the third position in the table. But there are some problems with this hash function. Since we are only looking at the first letter of each student ID, there might be more IDs starting with P than C. So more IDs will be mapped to the bin 0 than the bin 3. Second, different IDs can be hashed to the same value. For example, both Peter and Henry are mapped to bin 0. This is called a collision. It's very challenging to design a hash function to be uniformly distributed. And it is almost impossible to avoid collisions because we are mapping from a large range of objects to a smaller table. So we need some ways to solve the collision problem. There are two general strategies of resolutions. One is called open hashing. More specifically, we'll discuss the separate chaining approach, where collisions are resolved by extending the table with linked lists. The second strategy is called closed hashing, where it tries to find another position in the table. Within this strategy, we'll discuss two ways to find the next available positions: linear probing and quadratic probing. So what is separate chaining? It's just creating a linked list for each bin on the table. This means when we have a collision, we can just put the new entry in the front of the linked list. So why should we use the front and not the end? Because it's faster to access the front node in a linked list. And because of locality, we're most likely to access the new entry very soon. So what advantages do we have if we use separate chaining? First of all, you don't need a very big table since the linked list can grow dynamically and you get a more compact space. Second, you can actually store more items than the table size. Lastly, it's easy to implement the core functions find, insert, and delete because those are just the standard functions in linked lists. But we still have a disadvantage, which is we can't always guarantee constant runtime because we use linked lists. So one way to improve the runtime is we could use AVL trees to replace linked lists for each bin. This means we get O log n runtime. So here's how the table would look like if we used separate chaining. Let's assume the entries with Peter and Charlie are already in the table. They are the first node in their linked list. Now let's try to add a new entry with Henry's grade. The first letter H is equal to 104 in the ASCII table. So 104 mod 8 is equal to 0. So now we can insert Henry's entry at the front of the linked list. As you can see, if the linked list becomes too long, then the search and deletion will be expensive. Let's move on to the second strategy. So the second resolution is open addressing. For this, we need a bigger table for our data. That's because when we get a collision, we just keep trying different positions in the table until we find an empty bin. So we have two options for this. We can either do linear probing or quadratic probing. In linear probing, we just keep checking the adjacent bins until we find an empty one. In quadratic probing, we keep checking the bins with increasingly larger space in between. We'll see the pros and cons of these later. Let's start with linear probing. So linear probing just keeps moving forward one step at a time until it finds an empty bin. This means if we want to hash an empty object into a table and the bin is already occupied, then we keep looking in the next bin until we find an empty bin to store the data. If we get to the end of the array, then we just start at the beginning again. Let's see how we insert to a hash table using linear probing. First, let's add Peter to the table. We know it'll take the bin position 0. Then we add Henry's entry to the table. Since this ID is also mapped to the bin position 0, then using linear probing, we keep checking the next bin. In this case, bin 1 is still empty, so we put Henry's entry at bin position 1. Now we add Charlie's grade. Because this ID is mapped to 3 and bin 3 is still empty, we can simply store this entry at bin 3. We move on to add Katie's grade. In this case, we need to do linear probing again, so Katie's entry will be stored at bin 4. Linear probing will wrap around to start over from the top of the table. In this example, we add George's entry at the bin 7. If we want to add Will's grade, then since it is also mapped to bin 7, then linear probing will continue from the bin 0. Since bin 0 and bin 1 are already taken, Will's entry will be stored at bin 2. So for searching, we just start at the position that we think should have the object, looking forward and keep looking forward until we find it. The search fails if we get to an empty bin, or we've already traversed the whole table. For example, if we search for Will's entry using Will's ID, we'll start at the bin 7. Then we continue checking bin 0 and bin 1 until we find that bin 2. But if we try to search for Jack's entry, if Jack's ID is Jack 1, 2, 3, 4, 5, 6, it should be mapped to bin 2. So we check bin 2 and continue with bin 3 and 4, but we still can't find it. So we check bin 5, which is empty. And we know Jack's entry is not in this table. The search in linear probing depends on the empty bin to tell you whether you should end the search or not. But what if we want to erase some entry from the table? Does it create an empty bin? For erasing, we can't just remove an item from the table because an empty bin will break our search algorithm. For example, after we remove Charlie's entry, the bin 3 will be empty. Now if we search for Katie's entry, which is mapped to bin 3, we'll hit an empty bin there and end the search without finding it. But we know Katie's entry was stored at bin 4 according to linear probing. So we need to track which bins were originally empty and which bin became empty after deletion. This is exactly one of the solutions here. Instead of just leaving an empty bin, we mark it as a tombstone, so that the search algorithm knows it's empty, but the search should continue. Of course, the tombstone bin can be filled again if a new entry is mapped to that position. This solution is also called the lazy deletion because it leaves additional work for future operations. This additional work could accumulate until too many tombstones are in the table, or the performance could be compromised. Therefore, the hash table needs to be rehashed periodically to clean up the tombstones. If we want a complete erasing, then we may have to shift some entries to fill the empty bin after each erase. More specifically, after erasing an entry, we'll keep searching for the next entry which is supposed to fill that bin. For example, after we delete Charlie's entry, we need to try to fill the bin 3. So we need to find the next entry which is supposed to map to bin 3. Katie's entry is what we need. So we shift Katie's entry to bin 3. Then 4 becomes empty after this. We continue to this process until we hit an already empty bin. In this example, bin 5 is already empty, so we can stop there. With linear probing, we are always checking the adjacent bins. This means over time, the table will form some contiguous regions. With a contiguous region in the table, it is more likely to add new entries at the end of this region because any collisions in this region will be resolved by adding a new entry to the end of it. This will cause the region to grow even bigger, which in turn makes collision more likely to happen. The bigger those regions grow, the slower the table becomes. This is called the clustering problem. For linear probing, this is called the primary clustering. So to avoid the primary clustering problem, we can use quadratic probing instead. In quadratic probing, we check bins in increasing distance in between. More specifically, if we run into a collision at the position k, we try the positions k plus 1 to the power of 2, k plus 2 to the power of 2, and so on until we find an empty position in the table. So quadratic probing uses quadratic step sizes, while linear probing uses linear step sizes. But quadratic probing also has its own limitations. First, even if this avoided the primary clustering problem, the secondary clustering problem could still happen. Second, it's not guaranteed to find an empty bin, even if the table is not full. We'll see an example next. In this example, we'll add a few entries to this empty table. First, let's add Peter's entry to the table. It'll take bin 0. Then we add Henry's entry. There's a collision at bin 0. Let's try bin 1. Bin 1 is empty. We'll store Henry's entry there. We continue with Howard's entry, but now bin 0 and bin 1 are all taken. So by quadratic probing, we'll need to try bin 4. Bin 4 is empty, so we can store Howard's entry there. Now let's try to add Harris's entry. Because of collision, we need to probe from 0, 1, 4 and continue to 9, which is wraps over to bin 1. So let's continue with bin at 16, 2 rounds around the table, and still bin 0. Still not empty, we need to continue with 25, and it's at the bin 1. And you can continue the probing forever, but you will notice it only checks bins 0, 1, and 4. That's the limitation we mentioned in the last slide. So in summary, we talked about how to create a hash table using hash functions. And we also talked about how to maintain the hash table by resolving collisions. We can either extend the table by creating a linked list for each bin. This is called separate chaining. Or we try to find the next available bin for new entries. This is called open addressing. In open addressing, we discussed two strategies. One is linear probing, which just searches for the next bin and keeps looking until it finds an empty spot. The other is quadratic probing, which takes bigger steps in order to avoid the primary clustering problem. This concludes today's lecture. Have fun and happy coding. Bye bye.